Good afternoon, everyone, and thanks for attending the talk. My name is Sohaib. I'm a doctoral researcher at Tampere University, Finland, and I will be presenting our paper, Port Contention for Fun and Profit. This is a joint work between Tampere University, Finland, and Technical University of Havana, Cuba. Let's start by introducing a new side channel technique. We call it port smash. The technique targets the shared execution unit in simultaneous multithreading environments by monitoring the port execution usage of secret data-dependent control flows. Now you must be wondering from port contention, where does port smash comes from? So in this talk, I'm going to explain how our new side channel technique, how using port contention, we can actually create a timing side channel. This is a figure of a typical modern microarchitecture. It's been taken from the internet, so this should be pretty close to the actual architecture. As we all know, that traditional approaches to the microarchitecture design has focused more on the performance while limiting the silicon area and power dissipation. So more and more components are coming closer to the processor. For example, to reduce latencies for DRAM accesses, we got caches, and then for increasing throughputs, we have pipelining, different buffers in the pipelining stages. We have branch predictors, and we have speculative execution. On the instruction level parallelism, we can either have two different physical cores, like we can replicate the physical core, or we can use simultaneous multithreading. So the idea of SMT is to have two logical cores per physical core, where each logical core has its own architecture state, some set of registers, and they share some of the components of the physical core, such as the L1, L2 cache and execution engine in this example here. So due to the inherent nature of sharing resources in SMT architecture, security researchers started looking into it, that is it possible to leak sensitive information by having contention on these subsystems? In his pioneer work, Percival in 2005 demonstrated that a shared L1 data cache can leak information, and that was used to recover RSA key. And later on, IMU specific to the Pentium 4 processors, which was shared among logical cores, was targeted again on a real-world application. Then there was an attack on L1 instruction cache. Again, this was in SMT environment, a shared resource. And very recently, cache bleed, which instead of attacking the cache line, it was targeting offsets within the cache line. And finally, just last year, another shared resource, which is TLB, which is partially shared, was exploited to recover keys from ECDSA and RSA. And where we come, we are focusing on execution engine and how the contention on the ports can actually leak information. So let's zoom into the execution engine. So here's we have a simplified figure of how an execution engine looks like. On a high level, we have some instructions which are fetched, then they are decoded into smaller micro operations, and these micro operations are scheduled to be executed in different execution units. So the scheduler keeps a queue of these micro operations, and they are channeled through different ports to be executed. There is a port contention whenever two or more micro operations are issued to the same port. When we discovered first about this port contention, we started looking into related work, and we came across this very interesting blog post from Fogg. This mentioned about a tool called Covert Shotgun, and the idea was to try to find contention in subsystems and SMT architectures while pair of instructions were running. The blog post specifically mentioned about congestions due to execution unit and ports, and also caching of decoded micro operations. There were two open questions. First, which subsystems were getting congested by the pair of instructions? That is the source of leakage. And then whether that source of leakage could be used to create a side channel attack. So in other words, from covert channel to a side channel. And in port smash, we have tried to fill this research gap. So what is port smash? Again, it exploits the shared execution engine and creates a timing side channel due to port contention among two processes running on different logical cores and same physical core. So in order to empirically verify that there is indeed a port contention and there is some kind of a covert channel to secretly communicate, we performed an experiment on Intel Core Kaby processor. We selected a set of instructions based on their performance characteristics and also their port usage footprint. We created two processes on different logical cores. We call them Alice and Bob here. We decided that for sending a bit 0, we would use or execute instructions through port 1, and for sending a bit 1, we would execute instructions using port 5. So Alice starts listening on port 1, and then Bob executes some instructions on port 5, and Alice looks at the values of the latencies here. And then the same when Bob sends a 0, sorry, in this case. So it started issuing instructions on port 1, and there's a contention, so we can see the clock cycles went up. And this means there was a 0 being sent to Alice. So now that we have seen that there is some kind of a covert channel going on, and that two processes, Alice and Bob, on different logical cores, their performance depend on each other's port usage, can we use that to actually spy and create a timing side channel? So for that, we created a spy process here. You can see there are three different configurations here. One is on port 1, then there's port 5, and then there's port 0156, depending on the instructions that we have selected. The spy would, based on one of the configurations, start running these instructions while computing the latencies. We created a victim process. Here you can see there is a condition based on the secret bit value. It will either take the first branch or it will jump to the second branch if the bit value is 1. Now the attack starts when the spy is, when we run the spy. Here we configure the spy on port 1. So the spy is executing instructions on port 1 and waiting for the victim to start running its code. So when the victim is, when there is a bit 0, the victim will start executing the first part of the branch. And if you can see here, for both on port 1, there's a port contention. We get a timing side channel, and we have higher latencies here. And when the victim is on the other branch, the latencies are flat here. So from this timing side channel, we can infer which secret bit is being executed on the victim here. So another important aspect of port smash is that it has a very fine spatial resolution. If you look at, these are two different victims, but they have the similar port usage footprint because they execute the instructions based on this condition, either on port 1 or port 5 in this case. But there is a difference here. If you look at the memory footprint, this is different. So this one resides within one cache line, but the other one is between two different cache lines. So for this second victim, it is a good target for attacks such as flush and reload or other cache-based attack. But those attacks will not work on victims which reside within one cache line, for example. So for port smash, it doesn't really matter as long as we are able to identify the victim's port usage footprint. We, in order to prove that this is a real attack, or this is a attack, this is a side channel technique that can be used to attack real world applications. We performed an attack on TLS server and specifically the ECDSA signature generation. We chose the OpenSSL 110H branch because at that time it was the latest branch which has a secret dependent control flow in the code. And we actually fixed the branches like the future release branches with another work that we did previously. So the code always executes a double operation, and then it looks at value of a secret digit. If it's not 0, it will do add operation. So here we can see there is a conditional branch, and this is what we are going to exploit in the attack phase. So we started the attack by procuring TLS traces, and for that we queried multiple TLS sessions while there was a spy running in parallel monitoring one of the ports, which we actually selected based on experimentation. You can see here we have the TLS trace which has ECDH and ECDSA. Because we are interested in the ECDSA, we trimmed that out, and in the signal processing phase, we tried to recover the double and add operations. So here you can see after different steps of filtering, we are able to recover or clearly identify peaks as the add operations. So for example here, this ends at a add, which means we are able to learn at least 1 bit of leakage here. We did that for all the traces, and then built a partial nonce information and used that in our latest attack to recover the long-term key of TLS server. Here you can see for different trailing sequences of the point multiplication, we get really good distributions. So this information is provided enough resources. This information is enough to mount a successful lattice attack. And if you want more information about this, how the attack worked, you can also refer to the paper. So port smash is also effective against Intel SGX. So here you can see we have two different traces. On the top, we have point multiplication running inside an Intel SGX enclave, and on the bottom, we have a non-SGX version. So you can see we can clearly identify the add peaks. So because we are focusing on the execution engine, any isolation provided by the SGX on memory subsystem does not affect our side channel. Finally, we also propose some mitigations. we have learned the hard way in security community that we should always avoid conditional branches at all costs. So that I think is the best solution. Write the code that doesn't leak information. And as a result of this work, we were assigned a CVE, and we also contacted OpenSSL, and we backported the timing resistant implementation to older versions, which by the way was also another work we did on OpenSSL. In highly secure security critical applications, we can always disable SMT, so this attack will not work in environments where there is no SMT. And if there is a highly threaded application where we really need some kind of performance, so there are options where we can have isolation on the OS level. So we can conditionally turn off SMT, but it is hard to implement because we need to change at OS level and also on underlying libraries. So, and also it might be difficult to port to different architecture. So what is the takeaway? Port smash is a new side channel attack which can be used to attack real world applications. It can be configured using different ports. It is portable, so we just need an SMT architecture where we can run it. It has a very fine spatial resolution since we are talking about the micro-ops on the execution engine level, and then it doesn't require a lot of prerequisites. We don't need to know eviction sets and other things. We just have to run the SPI and configure it based on the architecture. And as microarchitectures are becoming more complex, there might be new side channel attacks coming on in the future. But the idea of this point is that now it's time for the security community and the architecture researchers to collaborate and to have better solutions where we don't have these kind of security problems. And finally, side channel analysis is still a practical and powerful tool to detect exploits or to find exploits in the software and finally mitigate them. And thanks everyone for listening to me, and I'm open for questions. And in the meantime, you can go on and just pull our proof of concept from this repo and just start smashing your ports. Thank you.
Thank you. So we have time for some questions. So maybe I'll take a quick question while people come up to the microphone. So there's like a whole gaggle of side channel attacks now available at this in the SMT setting, and you even allude to some in the talk. So in this, can you compare a little bit more about like why port smash would be better or worse? I mean, obviously there's the spatial thing, which is very nice, but in the victim code, for example, that you're looking at, other attacks would have been applicable as well, or not?
I mean, in the paper, we have a bit more detailed analysis on that, but one different thing in port smash is that we are not relying on the memory subsystem. So we are just focusing on the execution unit. So, and most of the attacks have been relying on the memory subsystem. So.
Hi, Guru Raj from Georgia Tech. Excellent talk, loud listening to it. Two questions. First, could you quickly maybe ballpark how much bitrate you're able to get through this versus, say, cache side channels? And if there's any difference in noise sensitivity? And second, did you subsequently trying to fit this in with the broad speculation-based attacks and trying to use this covert channel in that context? Thanks.
I'll answer the second question first. So I think there is a paper, Smother Spectre, which have actually used this port smash technique, and they combine it with the Spectre attack. So instead of cache-based attack. And on the first one, so we get a very fine resolution because, for example, in cache-based attacks where you're looking, so I think the cache bleed is one of the attacks which has the finest resolution because we are attacking the cache bank conflicts within the cache line. But here we are actually talking about micro operation level. So I think the resolution is quite good.
Time for one more question.
Hi, David Gens, UC Irvine. Really cool talk, interesting work. I have a technical question about the port assignments. You had a table where you showed the different instructions, and for add, there were different ports, right? The way that I understand it, it means that the add instruction can go to all of these ports.
Yeah.
Is that correct?
Yeah.
So in your second analysis, you showed that you extracted secrets from OpenSSL, I believe.
Yeah.
And it used the add instruction, right? And in the first analysis, you used instructions like CRC or instructions that go to the vector ports.
Okay.
So maybe could you elaborate on that?
Yeah. So your question is that in the attack we used add instruction. No, actually that add is a different add actually. So this is related to the implementation of the elliptic curve crypto. We have a double operation in ECC, and then we have an add operation. And within these add and double operation, we have different finite field operations like squares and multiplies, and those turn into instructions and then into micro-ops. For the sake of the attack, depending on the architecture, we have to do experiments on which port we get the better signal. So I think we used port 5 in this case, which worked for us.
Okay.
Yeah.
Thank you.
You're welcome.
Great. Why don't we thank the speaker one more time?
Thanks.